right. So we are now at the last talk of the last session, sadly. And so what I want to do is I want to talk a little bit more about games, and I want to try to connect them to what this was advertised as. And I do remember what it was advertised as. Okay, so hopefully this will work. Yes, okay. So we've talked about monovariants and invariants earlier today. So monovariant is something that can only change in one direction, and invariant is something that is always the same. Okay, and so it's often a challenge to find a good monovariant for problems. So I want to talk about zombies, and I will risk maybe making a political statement about zombies and what they can do to tell us about how we should run our societies. All right. So the way the zombie game, the zombie battle or apocalypse is played is if you share 2 or more walls with a zombie, you become a zombie, and once you're infected, you're always infected. So imagine we have a nice 4x4 grid, and we have 3 cells that are initially infected. So we'll say the bottom row is row 1, then row 2, row 3, row 4. The first column on the left will be column 1. So if you share 2 or more walls, you become infected. Does anybody get infected from this configuration?
Yes.
Okay, what row, what column?
You said row 1's on the top.
Row 1 is on the bottom.
Bottom. So row 4,
Row
column
4,
2.
Column 2.
Row 2, column 3.
Row
Sorry,
2.
row 3, column 3.
3. Anybody else?
And then
In
it
that,
keeps going.
okay, so initially only 2 people are infected. Now does anybody get infected?
Yes.
Yes. And so I think we can all see it's going to be row 3, column 4, row 2, column 3.
Yes.
So the zombie infection is spreading. We see that there's going to be another, the 2, but now things have stabilized. And so the zombie apocalypse has been contained. We have a nice L-shaped region of safety.
Okay.
Yep. Now, my question is, no matter what configuration, will there always be some safe area? Or if the zombies are going to capture everything, what's the minimum number of zombies I need to capture everything if they're positioned well? In this one, in a safe region, I have a column that's safe and I have a row that's safe. If the zombies don't capture everything, is there always a row and column that's safe? Well, what you would do with students is you would do lots of games and simulations. We're not going to do that right now. What I want to do is I want to just ask some extreme cases. I love extreme cases and building intuition. So right now, I need somebody who's willing to be a smartass.
Yeah.
Thank you. I didn't want to call out on you, but I was pretty sure you would step up.
Did look great.
So your grade for the course is on the line.
Okay.
So if you don't get this right, you're going to only get an A, not an A+. Give me the easiest configuration of which cells are infected that will guarantee that at some point in time, everybody's infected. The easiest configuration.
And that there are 3 infected cells? Or
No. You can choose which cells you want to infect. What is the easiest configuration of places to infect to guarantee that at some point in time, everybody will be infected and you want to be a smartass? The simplest configuration where you know at some point in time, everybody will be infected.
All even or all odd?
No.
Or all?
No, all, right? Everybody's infected, right? It's not hard to show that if everybody's infected, then at some point in time, everybody's infected. Now this, if it's an n by n board, this takes n squared zombies. That's a lot of money. Zombies aren't cheap. So then the question becomes, can we do it with less? And you then said,
Yes, even or odd.
so we could do like a checkerboard pattern. And if we do a checkerboard pattern, that's a 50% savings in zombies. You could, of course, gone back to everybody's infected and just remove 1 square. But doing this many times, I know people don't, they jump to the even odd, they jump to the checkerboard, which is great. So can somebody give me a configuration that they think is the fewest number to infect everybody? And where they might be? So you gave me the checkerboard worked. I could, so we could try the diagonal. Let's see what happens if we take the diagonal. What happens the next turn?
Both sides.
Both sides. And it just keeps propagating outward. Look at those beautiful animations, right? And so if we infect the main diagonal, everybody gets infected eventually. As an aside, you can connect this to the fires in Los Angeles. What should the humans have done to stop the diagonal infection? We see how the zombie infection is spreading, right?
Got rid of one
Shows
of these
it.
smaller diagonals?
Get rid of two diagonals around it, right? Cut out. And so you can connect this to what's going on with balancing conservation efforts with protection. If they had done some pre-burns, if they had just killed a bunch of people, they could have stopped the zombie apocalypse. So look, you're going to become a zombie anyway. At least this way you're not taking the rest of us down. And you still have plenty of time to shoot the people at the diagonals. So we've just shown that if you have the main diagonal infected, it's going to propagate outward. So the question is, can n-1 zombies, if they're cleverly positioned, get everybody? We started with 3 zombies on a 4x4 board, and for that configuration, it didn't work. But maybe there's a better configuration that would get everybody. How should we try to answer this? What could we do? Make the board smaller, gather data. So if we start off with a 1x1 board with nobody infected, not hard to analyze. If we start with a 2x2 board, we can only have 1 infected zombie. And we haven't used the word symmetry in at least 5 minutes, right? By symmetry, let's assume it's the upper right that's the zombie, because they're all the same if we rotate by 90 degrees. And we see that the zombie infection doesn't continue. We analyze tic-tac-toe. We can now get dividends from that. There's 3 configurations for 1 zombie on a 3x3 board, and now we need to place the second zombie on the 3x3 board. I'm not going to go through all the possibilities, but there's only 12 things to check, and you can show that none of them will get everybody. So we now have some data that n-1 does not seem to be enough on an n-by-n board. Maybe when n gets really large, some new behavior emerges. I do know situations where that happens, but I'm beginning to feel confident that n-1 zombies won't be enough. But that's not a proof. So let's find a way to prove this. So what I'm going to do is I'm going to look at the perimeter of the zombie nation. So the perimeter is just the part of the zombie nation that's on the outside. So imagine the 2 red squares are part of zombie nation, and I only care about the white square between them. And let's assume the white square is not infected, it's not a zombie. So I know that the cell above and below can't be infected. And so right now I have 2 walls that are part of the zombie perimeter, the left and the right wall. Okay? Once the cell becomes infected, those 2 walls became internal walls, but then I gained 2 external walls. So does everyone agree that if I had the configuration zombie, nothing, zombie, the perimeter doesn't change of the zombie nation?
Yes.
If I had 2 vertical, it would be the same analysis, right? What else do I have to look at for 2 zombies that are infected?
Kind of quarter.
Well, it can't be diagonal because they don't share a wall.
Oh.
So I could have one at north and one at,
South?
well, north and south would be the
Would be
same
the
as this, it
same.
would just be rotating 90. So what's the new configuration I have to think about? North and east or north and west. So I did north and west. So if I do north and west, then I have 2 external zombie walls, and then they become internal walls, and I get 2 new external walls. So the perimeter hasn't changed. So these are all the configurations where the new cell has 2 zombie neighbors. What do I have to look at next? 3 and 4. Well, 3 is not so bad. There's really, up to symmetry, only one way to do it. I have 3 exterior walls. I lose them and I gain 1 exterior wall, and the 3 previous exterior become interior. So the perimeter went down by 2. And the last case is really easy. You're surrounded by zombies. You lose 4 external walls and gain none. They all become internal walls. The perimeter goes down by 4. So notice that as the zombie infection progresses, the perimeter either stays the same, goes down by 2, or goes down by 4. The perimeter never increases.
So on this 4x4, so you're not looking at the corners?
In the 4x4, I only care about the walls with the cell that's becoming infected. I'm looking at the perimeter of the zombie nation. I don't care about what's going on in the other places. I'm just saying, what is the change when that cell becomes infected? Before it was infected, the 4 walls around it were all external walls in zombie nation. And now when the cell is infected, they're now all internal walls. So the perimeter of zombie nation went up. I'm sorry, went down by 4, went down by 4. I'm not looking at what's going on in the rest of the square.
Gotcha.
I just noticed that the perimeter never goes up, and it sometimes goes down. What's the perimeter of an n by n square? N squared. Not using any advanced mathematics here. What's the largest perimeter you could get if you have n minus 1 that are infected? Well, if they don't share any walls, that's the best you can do, and it would be 4 times n minus 1, or 4n minus 4. But if everybody's infected, well, that's perimeter 4n, right? And we know that the maximum perimeter, if I have n minus 1 zombies, is 4n minus 4. So at least 1 square is safe. Right? What do you think if there's only 1 safe square? Good or bad?
So that's being affected.
If there's only 1 square, then every square has at least how many neighbors?
2.
2. The corners have 2 neighbors. The other ones on the perimeter have 3 neighbors, and things in the interior have 4 neighbors. So if you have 1 square that's not infected, the best it could be is a corner, and it's still going to have 2 neighbors. What's going to happen? It's going to get infected. So what I can immediately deduce is, if only 1 square is safe, no, there has to be at least another square that's safe. Because if only 1 square was safe, it would have to be infected at the next moment. I am not going to see how far we can push this. I believe this is something for you to enjoy, or to enjoy with your students. Can you push this to there must be an entire row or column that's safe? And a lot of times in mathematics, you just need something to start the process. I know there's 1 square that's safe. What can I get from that? Is it just 1, or could it be actually a lot more than 1? Is there always going to be at least a row? It doesn't have to be. The 4n minus 4 only guarantees me 1 square that's safe. But we know it can't be just 1 square. Okay, so I will leave. There's lots of questions you can ask. I'm not going to do this. So I was fortunate to be a grad student at Princeton, and I got to know John Conway. You might know him from the Game of Life. Wonderful, fascinating person. And so here's a game that's called either Conway's Soldiers or Conway's Checkers. And again, because I'm doing this at Harvard and their endowment is not large enough, we will look at just drawing finite versions, but you really should be playing this on an infinite checkerboard. And the way it works is you can jump a piece horizontally or vertically. And when you jump a piece, the piece you jump over is removed from the board, and then you move to the new square. And so this move shows me that I can move a piece up 1 row. So I'm going to kind of like a mathematician. The top row that has checkers is row 0, row -1, row -2, row -3, and so on. And this shows you that it's possible in finitely many moves to have a checker go up to row 1. Okay? And again, you should imagine that the checkerboard goes infinitely to the left and the right, and infinitely down and up. Okay? Can anybody think of a way to get a checker to row 2?
I'm assuming the only way you can move is by jumping?
The only way you can move is jumping.
You can't do diagonal.
No diagonal jumps. You could analyze the game when you can do diagonal jumps, and that would be a very different game. You can only jump vertically and horizontally. Can you think of a way to get to row 2?
So would you bring, do
Yeah.
exactly what you did, bring that
Yep.
one up there,
Good.
and then you can jump horizontally to that next
Good.
column and then up.
Good. So I think I have that sketched here, but exactly what was said is you just have 2 vertical jumps next to each other, then do a horizontal jump, and now you have something in row 1 with something in row 2, I'm sorry, row 0 below it, which can then jump up. So you got something to row 2. There's other ways to get things to row 2. There's lots of things you can do. The next question, of course, is can you get something to row 3, to row 4, to row 5? How high can you get? Can you get arbitrarily high? You should hopefully have very little intuition on this. What should you do?
What data?
Collect data, right? If it's not symmetry, it's collect data, right? Gather data. Have the kids try and see how high they can go. I will say that after a while, somebody found how to do 3 without too much trouble. And one of you was really lucky, and you got a student who actually got up to 4. We were shocked. But nobody had a student who was able to get up to 5. Do you think that means you can't do 5, or just that maybe it's a very complicated move? Or sequence of moves? So what I want to do is I want to show you how Conway solved this problem while justifying the name for this seminar. Okay? So what we're going to do is we're going to take our infinite checkerboard, and what we're going to do is we're going to put weights on every square. And the weight is going to be relative to a target. So I'm going to take something, 5 units up at the point 0, 5. Now, I grew up outside of Boston. I love Boston. I can say I love New York, but it's the Yankees I hate. But I have to admit that there's one part of New York does very well relative to Boston. And this is being recorded, so be very careful what you say. What do you have to give credit to some part of New York over Boston?
Their city layout.
The city layout. Anybody who was driving in today, with the sun glaring at me in the morning and all the lane changes in a short period of time, it was amazing that there were no accidents. You have a nice grid. So we will only allow north-south moves and east-west moves, no diagonal moves. So if I want to get from one square to another, I count how many north-south, how many east-west moves do I need. The fewest number is the distance. So next to the target, everything, the north, south, east, west next to the target is all 1 step away. So it's x to the 1st power. Then there's a bunch of things that are 2 steps away. There could be 2 easts, there could be an east and a north, and so on. Those will be x squared. So the weight I'm going to give is x raised to the number of moves I need to get here. So over here for x to the 6th, I can go 1, 2, 3 and be underneath it, and then 1, 2, 3 and get up to it. And there's no way to do better. For the x to the 7th, I could go 1, 2 to get up to the same row, and then 1, 2, 3, 4, 5 to move over. And you can show that it doesn't matter which way you move, as long as you are only moving in one direction. You're never going to be stupid. And if I'm to the west of you, I'm not going to start off by moving further west. And so we're going to put a weight on each square. And so the first thing in the 0th row underneath it will be an x to the 5th, and x to the 6th, and x to the 7th. And I'm going to look at the total value of the board, and I'm going to look and see what happens to the value of the board as the game plays. And we're looking for monovariants. We're looking for things that only move in one direction. So what I'm going to do is I'm going to show that there's a choice of x so that the value of the board is never increasing. And then we'll show if you happen to have a piece at the target 5 units up, that is more value than the board starts with, or at least the same value as the board starts with, and thus you can't do it. Do you think you want x to be greater than 1 or less than 1? To have a finite value of the entire board.
just greater than one or less than one?
Right.
Well, I guess one, because then everything would be positive.
Okay, so if you take x to be 1, everything would be positive,
Yeah.
and this board is infinite to the left, right, and down. And so if the value of x was 1, what would be the value of the board?
One.
No, because you would have all these squares initially filled.
Oh.
So every
whatever's not filled, I don't know.
Well, so everything that has a check on it, you add its weight to the board value. Okay? So right now, everything in row 0 is filled. Everything in row -1 is filled. Everything in row -2 is filled. And I want the value of the board to be finite. If x equals 1, then every x, doesn't matter what power it is, it's going to be 1. What's going to be the value of the 0th row if x equals 1?
One.
No. Each cell is 1. Right?
Yeah.
This is going to be 1. 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 So how much value will the 0th row have? If every cell has a value of 1,
And you just add up that row.
right? And what would that be if you add 1 infinitely many times?
And plus, and
And we're adding it infinitely many times. 1 plus 1 plus 1 plus 1, infinitely often.
n times n plus one? I don't know.
No, what's 1 plus 1?
2,
Plus 1
3.
plus 1.
Oh, those are the counting numbers.
So if we add 1 infinitely often, what number do we get? We get infinity. We get infinity. So the first row would have a value of infinity. The second row would have a value of infinity. The third row would have a value of infinity. So if x is 1, the total value of the initial board is infinity. If x is greater than 1, then it's even worse. So what must be true about the value of x?
Less than 1.
Less than 1. So we know if this has any chance of working, we know x has to be at least some positive number less than 1. I don't know more, but I know it can't be greater than or equal to 1. So is there a choice of x that will give a finite value for the board, that will give me a monovariant as I do my game, and will have too much value assigned if a piece makes it up there? And so what we're going to do is try to calculate what's the value of the 0th row. So for the 0th row, we had something that was 5 units down, that's x to the 5th. Then we have 2x to the 6s, 2x to the 7s, 2x to the 8s, 2x to the 9s. So how many of you have seen the geometric series? So raise your hand if you've seen the geometric series. Okay. So it turns out that there is a formula for adding 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th. And so if you haven't seen this formula before, if it's been a while, that's okay. It turns out that there is a formula for that. And if we add all of this, it turns out we have exactly what it is. Okay, so this is where you just assume for now that this exists. If you're interested, I can easily show you a proof of this in 5-10 minutes, but let's just assume we have a formula for this. So this would be the value of the 0th row. And when the dust settles, you get 1 plus x, x to the 5th over 1 minus x. And now, let's think, this was the value of the 0th row. What would be the value of the negative first row? If you think about it, everything in the negative first row, how many more steps does it take to get to the target than from the row above it? 1 more. So you would take this value, and what would you multiply it by? Not -1, by x, because you take x to the power of the number of steps. Each move is now going to be 1 more step, so you can multiply everything by x. So the value of the negative first row is just x times this. What's the value of the negative second row?
X squared.
X squared. The negative third row? X cubed. So it turns out we just multiply all of these by different powers of x. That's another geometric series. What's better than using the geometric series formula? Using the geometric series formula twice. And when the dust settles, you get, here is the total value of the board. 1 plus x, x to the 5th over 1 minus x squared. Okay, how does this help us? There's two possible moves. When we move, we lose two pieces and we replace them with a piece from the jumping. And that piece could either be closer to the target or further from the target. If it's further from the target, given that we lost two pieces that were closer and ended up with something that was further, the value of the board goes down. Right? So the only way the value of the board could go up is when I jump, I land at a square that's closer to the target than the two pieces I've lost. So for example, imagine I have something at x to the 6th and x to the 5th. I jump over it and I now have something at x to the 4th. So I've replaced a value of x to the 5th and x to the 4th, that sum, with x to the 6th. I'm sorry, x to the 5th and x to the 6th with x to the 4th. So what I can do is I can say, let me set this equal to 0 so that there'll be no change and see what x leads to that. So I have x to the 4th minus x to the 5th minus x to the 6th. That means that the value of the board did not increase when I did this. And when the dust settles, when you factor out the x to the 4th, you just get 1 minus x squared. And you can see it doesn't matter if I did x to the 6th, x to the 5th, going to x to the 4th. I could have done x to the 10th, jumps over x to the 9th, and gives me x to the 8th. All that would change is now I would have an x to the 8th outside, and I need 1 minus x squared to be 0. That's the quadratic formula. So you can find the roots of that. And the roots are -1 plus or minus √5 over 2. But we know we need the board to have a positive weight. So we're going to take the positive square root. So we get -1 plus √5 over 2. This is the golden mean minus 1. So this was supposed to be using the Fibonacci numbers as a springboard. This is one of the strangest applications of the Fibonacci numbers. They come in constructing the monovariant for this. And so when you do this, if you now look at the initial board value, when you take x to be √5 minus 1 over 2, you get a value of 1. If you have something at a target of 0.4, the value of that is about 0.618. That's less than 1. So it could be possible that we could move a piece up to there and then have other pieces elsewhere on the board, and the total value could still be at most 1. If we move something all the way up to 0.5, the value of that is x to the 0, that's just 1. But the initial board for this value of x had a total value of 1. So if we can move something all the way up to there, the only way we could do that is if we jump every other piece and nothing remains. So there is no way to do this in finite time. And so as a nice exercise, you'll try to show that you can't do this in infinite time. Who here has really good vision? Can you see anything about the slide? Yeah, down on the bottom is something that it says possible in infinite game, and there's a web link. So somebody said, well, what if we allow ourselves some new interesting moves? And so the moves could be all the odds in a column simultaneously jump over all the evens in a column. And so if you start allowing yourself some strange infinite moves, then it is actually possible to get something up to the 5th spot. And this is a great example of trying to change the rules of the game and come up with something new. So 2 summers ago, I had some students look at generalizations of this. And one of the things we did is we put multiple pieces on the same square. And so what if you have several pieces? How high can you go? And the more pieces you have, how high can you go? Actually, I think that was last summer. People have also looked at higher dimensions. What if you have, instead of a plain version of the game, what if you have a box version of the game? So as always, when you have something like this, see how far you can push it. What if you add other kinds of moves? What if you allow a double jump? How far can you push it with something like that? And so the whole thing comes down to this idea of finding the right way to look at problems. And so, I might have forgotten to bring it. Let's see. I have it on.
I think I took it out. I think I left it.
I was going to show a modified Rubik's Cube, and there are lots of different cubes that you can look at, and they fell out of the back of the car. And for some of the cubes, they're really the same as a standard 3x3x3 cube, but you need to look at it at a 30-degree angle or something like that to see. And so much of math is finding the right way to look at the algebra. And we often train students to just mindlessly plug and chug, and if you give them something that's directly similar to what they've seen before, they know how to work on it. But if you give them something new, how do you convert this to something you know? And that's the challenge. How do we take this to something that we know? So what we proved last summer was if we now have m checkers in each box, that the height that you can get up to grows with the log of m base golden mean. Really nice result. And this was done by undergraduates, just taking something they had never seen before. And again, you don't need a lot of advanced math to start thinking about these things. I don't think we give students enough opportunities to be creative in schools. And there's often tremendous pressure to cover certain things and regurgitate. The older I've gotten, the less I care about what facts my students know, because you can look up facts. You don't want to be looking up too many facts. You want to know how to multiply numbers, but at some point, it's can you be creative? Can you ask good questions? And do you know what's out there so that you can then look up? So I know there's something called partial fractions and integration. I really hated that unit, but that might be useful for what I need to do right now. Let me go online and look up how to do partial fractions. So we have a few minutes left. So for the few minutes before Mary comes in, I want to talk about one last application with Fibonacci numbers. So did we talk about Zeckendorf's theorem? So this is a beautiful result. So I'm going to define the Fibonacci numbers 1, 2, 3, 5, and so on, where each one is the sum of the previous two. It turns out if you use this as your definition, then every integer can be written uniquely as a sum of non-adjacent Fibonacci numbers. So if you take 2024, here is one proof. Take the largest Fibonacci number less than equal to your number and start off by writing that. Then look at the remainder and take the largest Fibonacci number less than equal to that and keep going. Whenever you do this, you never took two adjacent numbers, because if you did, rather than subtracting them one after the other, you would have just subtracted their sum. So this is what's called the greedy algorithm. At every moment in time, you do what's best. I take my number, I throw away the largest Fibonacci number I can, look at what's left over. Throw away the largest Fibonacci number that I can, look at what's left over. Lather, rinse, repeat. Keep doing this. It is not the case that this is always the best thing you can do. There are some problems in mathematics where the greedy algorithm will trap you in a local optimal, not a global optimal. But for this, it does a very good job. Okay. So, interestingly, you can use this as another way of defining the Fibonacci numbers. So this is also one of the reasons why I wanted to end with this. We're so used to certain definitions. And the question is, why are we defining something this way? As mathematicians, we can define anything we want. The question is, when is it useful to introduce this definition? In baseball, what is a good agent trying to do for their client?
Get the best deal.
I'm sorry?
Get them the best deal.
Get them the best deal. And so how do you get somebody a really good deal? What do you need to do if you want to try to argue with management that this person is worth a lot of money?
Show that they're valuable.
Good. So how do you show somebody's valuable? The data. What data?
Baseball is full of it, right?
So give me something. I'm sorry?
ROV.
RBI.
RBI. And so you can say, this guy is really good at hitting people home and scoring runs batted and getting RBIs. And I said, yeah, the reason this guy is getting so many RBIs is he's batting behind people who have great on-base percentages. And my dead grandmother could get RBIs in a situation. Not, but You could say that that's not a good statistic because a lot of the RBIs is coming from the performance of people in front of them. So then what statistic might, so then you counter with a different statistic. And so you keep trying to find what statistic is the best one. So one of the worst statistics in baseball is the save statistic. Does anybody know how you get a save in baseball?
You come in as a pitcher when you're down. Is it down or
No,
up?
up.
Okay, you close the game out.
You close the game out.
Relief pitcher closes the game out.
And what about the lead?
Mm,
3 runs or less, you close the game out, or you pitch the final 3 innings and it doesn't matter how much of a lead you have. So I remember once the Rangers were playing the Orioles, and after 6 innings, the Rangers were up 14-3. So they had an 11-run lead. 3 innings to play, 3 outs an inning, that's 9 outs left. The Texas pitchers could have alternated home run out, and they would have won. That's how much the lead was. Texas scored 16 additional runs in the 7th and 8th inning, while their relief pitcher held the Orioles to 0, and he gets a save. Now, when you hear the word save, you think tremendous achievement. So that should not be considered a save. The game was not on, but if you pitch the final 3 innings, now it doesn't happen that often, but it does occasionally happen. So you want statistics that are meaningful. So whenever you're talking to students about what do we define, you want to think about why are we choosing to define something this way? Why did we make this choice? What does this give us? The standard definition of the Fibonaccis is you start either 0, 1 or 1, 1, and each is the sum of the previous 2. Here is a new definition of the Fibonacci numbers. It is the unique sequence such that every integer can be written uniquely as the sum of non-adjacent terms of the sequence. So let's take the number 1. Okay, I can get the number 1. I can't get anything else, so I have to add 2 if I want to get the number 2. Can I write 3 as the sum of non-adjacent terms of this sequence?
No.
No, I have to add 3. Can I write 4 as a sum of non-adjacent terms of this sequence?
Yes.
Yes, 4 is just 1 plus 3. Can I get 5 as a sum of non-adjacent terms of this sequence?
Yeah, well, of just those 3 numbers?
Of just those 3 numbers? No, so I have to add 5. Can I get 6 as a sum of non-adjacent terms of this sequence? 5 and 1. Can I get 7?
2 and 5.
2 and 5. Can I get 8?
No.
I have to add 8. Can I get 9?
Yeah.
8 and 1. Can I get 10?
8 and 2.
Can I get 11?
8 and 3.
Can I get 12?
8 and 3.
8, 3, and 1. Can I get 13? No, I have to add 13. So as a nice exercise, you can show this is an equivalent definition of the Fibonacci numbers.
Interesting.
They're the unique sequence that has this property. And you can prove every integer has a unique decomposition. This is called the Zeckendorf decomposition. And it turns out you can also show that if you look at all the ways to write a number as a sum of Fibonacci's, where you can have adjacent numbers, you can have repeats of numbers, that nothing uses fewer summons than the Zeckendorf. You can't do better than don't use anything twice, don't use anything adjacent. And the proof comes down to finding a monovariant. You can make a game related to this. We talked about the game Chomp, I think, last time, where we proved that player 2 has player 1 has a winning strategy. And did we talk about the Zeckendorf game last time? Okay, you can create a game based on the Fibonacci numbers in Zeckendorf's theorem. And when you do that, you can prove that player 2 has the winning strategy, except if you start off with just 2 tokens. Any other time player 2 has the winning strategy. And again, it involves this monovariant. It's trying to find the right way to look at things. This is extremely difficult. We often train people so that they're really good about solving problems similar to things they've seen. Trying to get people to think outside the box, to look at things new ways, to try to come up with good news statistics. Since we still have a few minutes, since Mary's not here, let me just quickly do one thing while we wait for Mary. As just, it's all about trying to find what is a good statistic. So hopefully this will work. Yes, okay. So let's assume 0 is less than x, less than equal to y, and I want to find the average. Actually, I'll say I want to find average. I won't use the word d. Can somebody give me a formula for the average? So I give you two numbers, give me a formula for the average. Any,
X plus Y over 2.
yeah, x plus y over 2. This is the canonical example that everybody who grades uses. Right? So I love this because this is a great way to talk to students about how do we choose what to study? What properties should an average have? So again, 0 less than x less than equal to y. What can you tell me about the average of x and y?
Should be between them, probably.
It should be between them. It shouldn't be smaller than x and it shouldn't be larger than y. I would like a property like that. And you can ask, are there other properties you want the average to have? And one of them is related to a word that we've used a lot.
Symmetry.
Symmetry. What should the relationship between the average of x and y and the average of y and x? They should be the same. And so your formula, x plus y over 2, it's really good. You could then start to ask, well, what would happen if I had more terms? What would be true? What I want to be true about their averaging? Now, as a corollary, what would the average of x with itself be? Right, so if it has to be between x and y, the only possible value for the average of x and x is x. That's good, right? Yeah, you got a 95 on the first test, you got a 95 on the second test, giving you an average of 30. So the question is, can you come up with other formulas that have these properties? So what if we define GM of x and y to be the square root of xy, or xy to the 1/2? 0 less than x less than equal to y. So the first question, is x less than equal to the square root of xy less than equal to y? Well, as x is less than equal to y, that implies x times x is less than equal to x times y is less than equal to y times y. So x squared is less than equal to xy is less than equal to y squared. So x is less than equal to the square root of xy is less than equal to y. So it turns out this is another good definition of average. So there is not a unique definition of average. And then you can compare. So we will say AM for the arithmetic mean of x and y is x plus y over 2, and GM for the geometric mean of x and y is the square root of x and y. And it turns out we just did 10,000 random pairs of x and y, and we notice the AM of x and y is always greater than equal to the geometric mean of x and y. And so this is a fun thing to prove. Now, consider x, y, and z with maybe 0 less than equal to x, less than equal to y, less than equal to z. I want to come up with some new kind of averaging. I like this idea of symmetry. So I want to look at things in pairs. I could have X and Y. What other pair could I have? Okay. And then I'm going to take this to some power A. I'm going to multiply it by some constant B. And I want to see, can I create an average like this? So can you think of any good choice of X, Y, and Z where you know what the answer should be? Okay, what should the answer be if you take 1, 2, 3? But you're doing the standard arithmetic average, right? Because you do 1 + 2 + 3 is 6. So what relation did we want? We wanted it to be sandwiched. Where should this mean live between?
That's line, let's see.
It should,
Between 0 and 1.
well, so the smallest of the numbers is X, the largest of the numbers is Z. The average should be at least X. And what should it be at most? Z. So can you think of a choice of X, Y, and Z where you'll know what the answer is? All ones or all
Zeros,
all.
all the same.
So if X equals Y equals Z, it is just X, right? So we would have B times X squared to the A has to be X. I'm sorry, not X squared. How many X squareds would I have?
3.
3. Right? So I would need that to equal X. So I would get B times 3 to the A, X to the 2A equals X. So what do you think? So A is a half, and B is 1/√3. So if I look at it like that, that gives me something to try. Another way I could look at it is I could look at it as B times XY to the A plus XZ to the A plus YZ to the A, where I take each one to the 8th power and then combine. And if I do it like that, if X equals Y equals Z, then X would have to be 3B X squared to the A. So now B would be 1/3 and A would be 1/2. So all of a sudden we see that there's a couple of choices of ways to average 3 numbers. And different choices will have different benefits. How many of you teach statistics at all? As you talk a little bit about the difference between the mean and the median. Yeah, the median is insensitive really to one more person coming in, but the mean can be changed greatly. Do you want to be in a situation where one person changes things greatly or not? And so there's pluses and minuses to the different choices. What I like about something like this is you can leave this somewhat open-ended for the kids. Which way should we define a mean for 3 people? What are the advantages? What are the disadvantages? That we have choices in terms of what we study. All right, so this is a good place to stop. Let me just stop the recording.